In large language models, or LLMs, performing complex reasoning tasks often requires generating long sequences of tokens. This is because reasoning involves multiple steps of thinking, like breaking down a problem and building toward a solution, which can lead to more accurate answers. However, this process is computationally expensive, especially during the decoding phase, where the model generates each new token one at a time while keeping track of all previous ones. This makes it memory-intensive and slow, growing even worse as models get larger or sequences get longer. The research paper introduces a new approach called SplitReason, which aims to make this process more efficient without sacrificing accuracy. The key idea is to use two models, a smaller, faster one for most of the work, and a larger, more powerful one only for the toughest parts. For example, they use a 1.5 billion parameter model as the small one and a 32 billion parameter model as the large one. The small model handles the bulk of the reasoning, generating tokens quickly, but when it encounters a particularly challenging segment, something that might require deeper insight or more complex calculations, it learns to hand off that part to the big model. To make this work, the researchers first identified which parts of the reasoning process are difficult. They did this by annotating over 18,000 reasoning traces from a dataset called OpenR1 Math-220K. Which consists of chain-of-thought examples for math problems. In a chain of thought, the model explains its reasoning step by step before giving the final answer. By marking the hard segments in these traces, they created a labeled dataset to train the small model. The training process involves two main techniques: supervised fine-tuning, or SFT, and reinforcement learning fine-tuning, or RLFT. In SFT, the small model is trained on the annotated data to generate the reasoning steps accurately and to insert special tags when it needs help. Specifically, it learns to output a tag like less than big model greater than when it detects a difficult part, which signals the system to switch to the large model. Once the large model generates the necessary segment, it might end with a less than big model greater than tag, allowing the small model to take back control. RLFT adds another layer by using reinforcement learning to fine-tune the model based on rewards. For instance, the model gets rewarded for correctly identifying when to offload and for maintaining overall accuracy, encouraging it to make smart decisions about when to use the big model. In practice, here's how SplitReason operates during inference. The small model starts by processing the question and generating an initial chain of thought. If it hits a tough spot, like solving a complex equation or making a subtle logical leap, it emits the less than big model greater than tag. This triggers the large model to take over, generating the difficult segment in what's called decode mode. Meanwhile, the small model prepares to continue by prefilling on the large model's output. Once the large model finishes, the small model checks if it can resume, potentially repeating the process if more challenges arise. This back and forth minimizes the use of the expensive large model, which is much slower for decoding, about 15 tokens per second compared to the small model's 150 tokens per second. The benefits are significant. On the AMY24 dataset, a challenging math competition benchmark, SplitReason improved reasoning accuracy by 24% and 28.3% in different setups, while only offloading 1.35% and 5% of the total generated tokens, respectively. This means most of the work is done by the efficient small model, leading to faster overall processing times. For instance, using the small model for the majority cuts down end-to-end time dramatically compared to relying solely on the large model. Figure 1 in the paper visualizes this concept, showing how SplitReason intelligently decides when to offload, resulting in a speedup while boosting accuracy over just using the small model alone. Figure 2 provides a detailed example. The small model generates text until it needs help, then the large model steps in, and they switch roles seamlessly. This approach addresses a common trade-off in LLMs. Larger models are better at complex tasks but are resource-heavy, while smaller ones are quick but might struggle with harder problems. By combining them, SplitReason makes reasoning more accessible and efficient, especially for tasks like math problem solving where accuracy matters. The researchers also highlight that this method reduces the memory burden. Normally, generating long sequences requires maintaining a key value cache that grows quadratically with length, but by keeping most generation on the small model, they mitigate that issue. Overall, SplitReason demonstrates that not all parts of reasoning are equally demanding, and by teaching a smaller model to recognize and delegate the hard parts, we can achieve high performance with lower costs. The team has open-sourced their model, dataset, code, and logs, making it easier for others to build on this idea and apply it to other reasoning tasks beyond math, potentially in areas like science or logic puzzles. This innovation is particularly timely as LLMs continue to grow in size and capability, but so do the demands on computing resources. By optimizing how we use these models, we can make advanced AI more practical for everyday applications.